Hello, I am Dr. Deepti and we are looking at different concepts from maths under the heading Decreations Mathematics. Recently we have been learning concepts from linear algebra, especially the concept of linear combination, linear independence and dependence. Now let us solve two questions based on it. We have been given a set of vectors, namely v1 is 1, 1, 1, v2 is 1, 2, 0, and v3 is 0, minus 1, 2. And we need to check whether these vectors are linearly independent. So let us recall the concepts we have already learned. We had learnt about linear combination. So here you can see the generic form of the vector equation when we look at linear combination. Then we had looked at the concept of linear independence, and we know that given set of vectors going from v1 to vk will be called linearly independent if this particular equation c1v1 plus c2v2 plus dot 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 plus vk is equal to 0 has only a trivial solution. So here we know that on the right hand side it has to be 0, and this particular equation is true only if all the scalars c1, c2 dot 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 ck are 0 simultaneously. So now let us go back to our question. So here when you want to check that whether this particular set is linearly independent, you need to basically find out the coefficients. So this is our general condition, C1V1 plus C2V2 plus C3V3 is equal to 0. Now, let us consider the first term, C1 into V1. So, C1 into the first component of V1, which is 1, that gives you C1 itself. Then C2 into V2. So, C2 into first component of V2, that gives you C2 itself. Now C3 into V3. Notice that first component of V3 is 0. So there is no term here involving C3. So we get our first equation, C1 plus C2 is equal to 0. Similarly, we move on to the second components of all the three vectors. So C1V1 will give us C1 into second component, which is 1. So C1 itself. Similarly, C2 into V2 will give us C2 into 2. So second component is 2C2. Similarly, C3V3 will give us C3 into minus 1. So minus C3. So what is the equation? C1 plus 2C2 minus C3 is equal to 0. Now let's go to the third equation. So again C1 into V1. So C1 into plus 1 again. So C1 is there. C2 into V2. So here C2 into 0. So no term. And C3 into V3. This particular term. So C3 into 2. So plus 2C3 is equal to 0. So we have a set of three equations. Now you can solve them using a matrix or Gauss method, and when you will solve it, you will realize that it has, this particular system of equations has a unique solution, namely C1 is equal to 0, C2 is equal to 0 and C3 is equal to 0. So when you look at this, you will realize that this is in fact the trivial solution. So what we had seen earlier in case of linear independence, this condition that all the scalars have to be 0 is being satisfied. Hence, we can say that the set of vectors v1, v2, v3 is linearly independent. Now let's do an interesting thing. Let us just change this third component of third vector. Everything else remains the same. And let us see what happens. So we have changed this third component. Again we have got a set of vectors, we follow the same procedure. So looking at C1 V1 plus C2 V2 plus C3 V3 is equal to 0. I'll show it to you for the first one. The rest of it you can understand. So C1 into V1. So C1 into first component of first vector, which is 1. So C1 itself, plus C2 into V2. So C2 into first component of first vector, which is 1. So that gives you C2 itself, plus C3 V3, which is C3 into 0. So that vanishes. So the equation is C1 plus C2 is equal to 0. Similarly, you can obtain two more equations for the second component as well as the third component for all the vectors. Now, when you obtain this set of equation and when you solve it, you will realize that even though there was a slight change, the first vector was same, second vector was identical, only change was in V3. We had just changed this third component, but the system of equations it led to is very different. Why? Because when you will solve it, you will realize that this has infinitely many solutions. That means there are several non-zero combinations of the scalars C1, C2, C3 such that linear combination of the vectors V1, V2 and V3 is equal to the zero vector. So C1 is equal to -1, C2 is equal to +1, C3 is equal to +1. This can also be one of the combination. Try substituting it and you will realize that it gives you 0. So let's try it. So -1 into 1 is so -1. 1 into 2 is 2. And 1 into 0. That gives us 0. Similarly, you will realize that you are going to get 0 for all the three counterparts, and hence in this case there are non-zero scalars which are giving you this particular vector equation C1 V1 plus C2 V2 plus C3 V3 is equal to 0. This means that we are going back to the linear dependence condition. If you remember, when we had looked at linearly dependent vectors, we had seen this condition. And that is what is true here. So this set of vectors is linearly dependent. Thank you.